Let's make our understanding of recursive function calls a little bit more sophisticated by introducing the idea of mutual recursion. Mutual recursion is the topic taken up in Chapter 13.5, Section 5 of Chapter 13. The idea of mutual recursion is to not have just one method that calls itself, but to have a sequence of methods that potentially call themselves in a circle. And in this way we get recursion, but it's not recursion because a function calls itself. It's recursion because function A calls function B calls function C, then function C calls function A again. And that can continue indefinitely, again, unless we have a base case. And if for recursion to work, each time we call this function, this chain of functions, this mutual recursive set of methods, we need the problem to get a little bit smaller. Now, a really elegant way of doing mutual recursion is to do what's called a syntax parse tree. And you can do this in a lot of different domains, but let's look at it in the context of arithmetic expressions. So we know that arithmetic expressions can take a particular form, and we're going to look at a simplified set of them. And that simplified set are expressions that have integers, plus and minus, times and division, and then parentheses. And we also know that a very important part of being able to evaluate these functions correctly is to have a consistent set of ordering of these operations, knowing that parentheses take precedence over multiplication, and multiplication takes precedence over addition and subtraction. So as a result, writing an algorithm that computes the answers to these expressions can be quite complicated. It turns out that this is actually a very good application of recursion, because recursion takes the idea of some grammar that we can impose on these expressions and can solve it with knowledge of that grammar. So let's take a look at how we might implement that. Move right. For starters, let's make sure that we understand the syntax for our language. And we're going to look at this syntax in a particular abstract way. Let's start with the idea of expressions. So we're going to name three things. We're going to have expressions, terms, and factors. And they're each, they're just names for these different chunks of our grammar. But what an expression is going to be is an expression is either going to be a term by itself, or it's going to be a term added to a term, or it's going to be a term subtracted from a term. And that can have a sequence of things. So if you look at this diagram, you can see the only way to get through from the left side to the right side of an expression is by going through a term or by looping through the pluses and minuses. And you can see by the structure of this diagram, you only have a term by itself or a pair of terms on either side of a plus or minus side. Similarly, a term can only be a factor by itself or a factor that is two factors that are on either sides of a times sign, or two factors that are on either side of a divided sign, or a sequence of factors that have one times or divided between each of them. Again, the only way you can get through this diagram is by following these arrows possibly multiple times. And then finally, what a factor is going to be is a factor is either going to be a number, that's our base case, or it's going to be a parenthesis on one side of an expression and on the other side the other kind of parenthesis, close parenthesis. And you can see that there's recursive structure here because an expression depends on a term depends on a factor, and a factor depends on an expression. But you can also see that there's a potential for a base case here in the final number that gets evaluated by a factor. That's the structure of our language that we want to be able to evaluate. Move right. So just to reiterate what I said, an expression can be broken down into a sequence of terms separated by a plus or minus. Each term can be broken down by a sequence of factors separated by a times or divided sign. Each factor is either a parenthesized expression or a number. And we can then generate, again, we don't do this in the code, but we can generate a syntax tree that represents the parsing of our particular arithmetic expression. Let's take a look at some of those. Move right. Thank you. Okay, so here we've got a couple expressions. On the left, the way you read these is you read these on the bottom, and we have two expressions, and I just want to show how these expressions get parsed, how they get interpreted by our parse tree by building a tree that characterizes each section of the arithmetic expression with a grammatical element. This is very similar to like how you might parse an English sentence using parts of speech. Maybe you did that in a grammar class growing up. It's a similar thing, but we're going to have the algorithm do it automatically for us. The key thing to recognize is that we're always going to start at the top with an expression, because at the very simplest, our expression can just be a single number. And we know that an expression can handle that. And if an expression can handle a single number, or it can handle parentheses that are around a term, around a factor. Okay, so if we look on the left, we have the expression 3 plus 4 times 5. And you can see that as we build up this grammar tree, each one of those numbers is first going to be interpreted as a number. Okay, that makes a lot of sense. Because they're separated by the characters that they're separated by, the plus sign and the times sign, the 3 and the 4 are going to be interpreted as factors, and then the 3 will be interpreted as a term. The right side will be interpreted as a number, and then a factor times a factor becoming a term. And then finally, you'll get a term plus a term that becomes the expression at the top. And in this way, you can see we're honoring the order of operations. Similarly, on the right, you can see how the parentheses get brought up to the top in the interpretation of our expression. They become either side of an expression, a factor on either side of the expression. Anyway, you can see it. The numbers are there, and we've got the factors and terms. And you can see that in some cases, there's a deep recursion, and in other cases, there's not so much recursion. Move right. So in the mutual recursion, we're going to use these cooperating method calls, which are going to call each other repeatedly in order to get the answer. So what we're going to do is we're going to walk through the methods here, and then we can look at it in more depth. All right, so we're going to need 3 methods. We're going to need a method that is called get expression value, and that's going to take in, that's going to consume some of the characters in our string, and it's going to return the numeric value of that expression, or that term, or that factor. Okay, and these are all going to call each other recursively. Move right. Let's start with the get expression value. Now first, to understand how this code is called, when the class is initialized, the expression evaluator class, it gets evaluated with a constructor, and the constructor is passed in the string that we're being asked to evaluate. So before we even get here, we've already called the constructor, we've given the class the string that we're trying to parse, and that string is being, there's an internal function called tokenizer that is doing the work for us of breaking down that string into the different chunks, because we have to make sure that like a 2-digit number is recognized as one number, and we are separating out the non-numeric digits from the operators, etc. So first thing I want you to see is I want you to see that when we call our expression value, we recognize that our expression value is either a term, or it's a term plus or minus another term. So the first thing that we do is we make our recursive call. We say, well, we know we have to have at least one term for this thing to be an expression. So let me get the term value of the strings that are present in my tokenizer. That's a recursive call. We assume that we get that, and we get the value back. Now we start a loop that's going to go through each of the different operands on each side of the plus or the minus, and then add them or subtract them up. So as long as we're not done, we're going to take a look at the next character that's coming down our string. The tokenizer is going to help us look at that next character. We're just going to peek at the next character. We're not going to pull it off, so it's going to stay there in this stream that's coming in. And we're going to look at it. We're going to say, okay, what's coming next? If what's coming next is a plus or a minus, then we can keep doing the work of the expression. What we'll do is we'll say, oh, we know what's coming next is the plus or the minus. So we're going to go ahead and consume that token by calling tokenizer.nextToken. That'll pull that plus or minus that we know is there off of our string. And now when we call getTermValue, then we're going to take what's left of that string and recursively allow the term value to pull off the next term from it. So we'll get value 2. And then now, depending on whether what we pulled off of our string was a plus or a minus, then we're going to add or we're going to subtract those two values together. And we'll keep doing this, assuming that we're pulling a plus or checking to see whether or not we're pulling a plus or a minus off. And if at some point there's not a plus or a minus, then we're done doing our expression and we just set done equal to true and we return. So we recursively pull a term, add or subtract it, pull a term, add or subtract it, until we're done with our expression, assuming that we can get these values of the term, because that's our smaller problem. Move right. Now the get term value method is almost exactly the same code, except instead of the plus or the minus, we have a times and a divided by instead. So let's go back and look at that for a second. Move left. So in get term value, this is the get expression value, we're going to replace the pluses and minuses with the times and divided by and get almost exactly the same code, structured very similarly. Move right. Our get factor value, however, looks a little different because it isn't structured the same way. Rather than having operands on either side of an operator, like a plus or a minus, times or divide, in the factor value we have parentheses on either side of an expression. So we have to structure the code a little differently. And in this case, what we're going to do is we're going to peek ahead to the next character to be consumed. And if it's a parenthesis, well, we know that what we're looking at is a parenthesis, an expression, and a parenthesis. So we go ahead and consume that, throw away, take that left paren off of our string. And then we say value equals get expression value. We call a recursive call to consume as many characters as we need to in order to solve the expression parse. And then finally, we pull the close parenthesis off on the right side, returning whatever value we ended up with. Now, the other option is that we didn't have parentheses. In that case, what we do is we're going to pull off the next token off of our string. We're going to turn it into an integer, transforming a string into an integer, and just return that value right away. Move right. So as we do mutual recursion, parsing through an expression like paren 3 plus 4 paren times 5, the first thing that we're going to do is we're going to call expression value, get expression value, because that's the way we always kick this off. That's the highest level of our parse tree. That's going to call term value, and term value is going to call factor value, and factor value is going to recognize that we're starting with a parenthesis. And so it's going to pull off that parenthesis, and it's going to allow the expression within there to be evaluated to 7. 7 will be returned, we'll consume the right parenthesis, and then we'll pass 7 back up the chain. Get term value will consume the times and the 5, and will return 35. And expression value will get that result as a return value back, have the 35, and return that as the answer. So recursion is going to terminate when we have consumed all the tokens of this input string. So now let's take a look at the code and see if we can walk through and see how this works. And let's see what it would look like to add one more operator to our parse tree. Great.